Hello physics students. In this video, we're going to learn more about vertical circles. Now we already learned about vertical circles in the last physics class, but what we learned wasn't complete because the notes were already long enough, there were already enough topics and concepts, so I didn't want to overburden your mind by giving you the full complete picture. So we're going to get that today. Before we jump into that, let's just review what we learned in the last physics class. If I take something on the end of a string like this and I spin it vertically, in other words, in the vertical plane like this, then what we learned is that the string tension holding this in circular motion is greater at the bottom than at the top. And the reason for that, well, there are two reasons. One is that at the bottom, the object's moving faster because of the gravitational effects on the way down. We used energy conservation to exactly quantify that. So we said up here, there was both gravitational potential energy and kinetic energy. Down here, the potential energy went away, so that number of joules had to go into giving extra kinetic energy down here. So K plus UG equaled K down here, higher velocity. And from mv squared over r, higher velocity means more force required to keep something in a circle. The other reason is that up here, the force of gravity is working together with the string tension, both in the downward direction. So the string doesn't have to pull as hard because it's getting help from the force of gravity, the weight of the object in circular motion. Down here, the force of gravity pulls the object away from the center of the circle. So it's kind of like the string has to overcome that and then provide extra force to keep it in a circular path. So higher velocity, and the fact that gravity doesn't help at the bottom but hinders in keeping in the circular motion contribute both to more force at the bottom. But what we missed yesterday is that when I spin this in circular motion, there is a requirement for the velocity at the top, not at the bottom. At the bottom, I could spin this at any speed I want and there's no problem. In fact, I could have zero velocity and it hangs like this without falling. At the top though, if I let this go, it falls. So there's nothing to hold this up here. So if I have zero velocity, then falls. And even if I have a little bit of velocity, but not enough, watch what happens. See that? I tossed it a little bit to the side and it fell in a parabola and it did not maintain a circular path. So I need at least a certain amount of velocity up there, a minimum to keep this in a circular path. If I go slow this down, faster is fine, but if I slow this down enough, the circle collapses. So what we're going to do today is we're going to calculate what's that minimum speed that you need at the top to maintain a circular path. And then we're going to calculate and analyze the forces when you're slower than that speed and when you're faster than that speed. So that's what's happening. Before I go on, I just want to show you just kind of a classic physics demonstration. It's similar to this, but maybe a little bit more dramatic. What I have here is a cup on a string, and I'm going to put a little water in here. It's going to demonstrate this minimum velocity with a little bit more, how should I say, a little more risk, because if I go too slow, the water will spill. So now if I go like this and go there, water doesn't spill. If I go too slow, well, water spills, right? So why does that happen? Well, because if I just take a cup with a ball, I don't want to do it with the water, I don't want to get the carpet underneath all wet. But what essentially is happening is if, forget about circular motion, let's just think about linear motion. If I go like this and let this go, the ball falls out of the cup. Obviously, there's nothing underneath holding it. But if I accelerate this down fast enough, I can have the ball not fall out of the cup. Here's too slow, right? So you see that when I go like this, the ball accelerates at 9.8. Maybe I make this accelerate at 4. So now what's happening is this falls this amount and the cup only goes this far. So it's kind of like racing ahead. However, if I make this cup accelerate at more than 9.8, then what can happen is the ball stayed in the cup. Or, more accurately, what happened was the ball accelerates at 9.8, maybe it falls to here, but the cup, I'm going to force it to accelerate more than 9.8, so it's over here. So what happens is it pushes the ball down and the ball is not able to accelerate out of the cup. And that's essentially what's happening with the water. And that's also what happens now in the case of the water. When I spun it, if I go in a vertical circle and I go and I let the ball go without the cup, it'll go in a parabola as we studied in projectile motion. If at the same time what happens is while this follows the parabolic path like this maybe, if I take this cup and I make it accelerate to here faster than the parabola, the water gets pushed by the bottom of the cup and it stays in. So that's essentially from an acceleration perspective. But now let's look at forces, the way we're going to solve for that critical speed, that minimum speed I need at the top to maintain the circular orbit. So here are our notes: vertical circles 2, critical speed, which we give a symbol of V with a subscript C for critical. So the definition, V critical, is the speed at which the centripetal force equals the force of gravity at the top of a vertical circle. I'll say a little bit more about the meaning of this in a second. So here's the first case. I'm going with exactly the critical speed. What I want to do is analyze the forces so I can calculate what's the minimum speed I need. Less, no circle. More, okay. So here's our vertical circle. We slow the circle down, and then at the bottom, there's always upward force. Here I'm going to use normal force instead of yesterday I used string tension. Well, now we're looking at a situation of maybe a roller coaster, and you're sitting down at the bottom and you go in a vertical circle. What's holding you up is not a string going up to the center of the roller coaster's circular arc, but the seat under you pushing you up. And when something pushes you up like that is a normal force. So we could have string tension like yesterday. Today we're going to look at just normal force with a roller coaster, just to give you a little variety so you are ready for different permutations of these problems. Now at the top, when I go slower and slower, there's a force up here, and then it gets smaller and smaller the slower I go. And then when at the critical speed, what happens is that other force vanishes at the top. And it's only the force of gravity that's keeping this in circular motion, because we always need a force toward the center of the circle. That's provided only by gravity at the critical speed. That's the key physics there. Now, so we start with our equation. Now let me say more about this. I said this in class yesterday and even before when we first learned about circular motion. This is not saying there are two forces that are equal, that are balancing. A lot of times physics equations, when you have one thing equals another, that's two forces that balance. Not here. There are no two forces. There's only one. And it happens to provide enough to keep us in circular motion. So that's what this equation is saying. There's one force, and it is sufficient to keep us in circular motion, so we have circular motion. Now, all centripetal forces must have a magnitude of mv squared over r. So I put that in for Fc, and then force of gravity is always mg near the surface of the Earth. And then what I do is I just solve for v. The mass drops out, I multiply the r to the other side, and I take the square root, and there's the minimum speed I need to maintain that vertical circle. So just no mass, okay? And also just radius of curvature and 9.8, and that's it. Now that's important, no mass, because like when you're dealing with roller coasters or Ferris wheels, we're going to talk about later, then the mass of the occupants doesn't matter. Everyone needs the same minimum speed at the peak to maintain a circular motion. So you don't have to worry about the mass of the occupants, just the radius of the loop you're performing and 9.8. So let me create, or go ahead and take a pause here and copy these notes down in your notebook if you need time to catch up. All right, let's continue on. So you can go greater than the critical speed. Obviously, that's what I was doing when I was whirling that tape around in the water. So that's the next bit of notes. We already studied this in class yesterday, but I'm going to put this up here anyway, just so our notes are fully complete of all the situations at the top of a circular arc. So we're faster than the critical speed. What can happen is the mass on a string, which we studied in class yesterday, but also, as I just mentioned, a roller coaster. Imagine you're going in a loop, you're coming down, everyone's screaming, and you go upside down, right? So what you need is at least the critical speed so the people don't fall out of the tape when it collapses, so people don't fall out of the roller coaster. Well, they have harnesses, but you still want to just have that as a extra safety mechanism. You want to go faster than the critical speed, although I imagine some roller coasters, they probably stopped up there to scare people. But generally speaking, you want to go faster than the critical speed. That means that gravity is not enough. We need an extra force. In this case, you're under here and the seat is up here, so it's pushing on you downward, and that's a normal force instead of a string tension. So just like in our notes yesterday, two forces up there. So here's the physics. We require a centripetal force when we're in circular motion. What's providing it? In this case, the normal force and gravity together, because they're both down, so we have a plus sign here. They're adding together to keep us in circular motion. Plugging in the details, mv squared over r, that's what the centripetal force always has to be. Then we've got our normal force, and gravity is mg. So we solve for this normal force, and this is the force on the occupants, mv squared over r minus mg. And so the force up there is less than your body weight, or actually, no, it could be more, depending on how fast you go. So let me go ahead and we'll pause the video a little bit. Go ahead and pause it and take a moment to copy these notes down in your notebook if you need it. All right, so at the critical speed, greater than the critical speed, how about if we go less than the critical speed? Well, in the case of the tape, we saw it can't be done. So what you need to do is, because this circle will collapse like this, only if you don't have a force underneath to support this going in a circle, a circular path less than the critical speed. So physically what that means when you go less than the critical speed, it's like you're in a Ferris wheel. The seat's under you, holding you up, and then you go up over the top of the Ferris wheel slow enough so that you don't come out of the seat. Not really truly what's happening. If you go too fast, then what would happen is your body would follow this path like this, and the seat would accelerate out from under you, and you would land and crash, so that'd be bad, right? So you want to maintain slower than that so that you don't fly in this parabolic path. Another possibility, besides the Ferris wheel, is whenever you're in a car and you're cresting over the top of the hill. You're going, now that top of the hill could approximate a circle, and you're going to go less than the critical speed, hopefully, so you don't become airborne. So what's going on in terms of the forces? Now, gravity is too much force. Again, this would collapse like this to maintain that circular arc. So you need to lessen that force a little bit with the normal force underneath you so that you have the right number of newtons to maintain that circular arc. So that's the physics, the forces. But gravity must be greater, again, because we need a centripetal force and net force toward the center of the circle. So the centripetal force is these two subtracted from each other. This minus that one. It's the net force, right? So then we plug in the pieces. Centripetal force, so is mv squared over r. Gravity is mg. And the normal force is some unknown. So we solve for normal force, add it to this side, and then subtract the mv squared over r to the other side, and there's the normal force. When you go over that crest, you feel the support force under you less than your body weight. So if you're a 100-pound person, maybe you only feel 80 pounds of support force underneath you, the subtracting of mv squared over r. So if you need a moment to catch up, let's pause for a second and copy these notes down. All right, so that's vertical circles too. Now, I just want to give you one practical example. We talked about Ferris wheels and cars cresting a hill, roller coasters, but I could tell you a little story. When I was a kid, I remember I was real little, real small, and one of my uncles would take us swimming sometimes. And so he had this little Volkswagen Beetle, cute little car, and he would take us down this road through the woods, and it was up and down like this, windy, and he would go really fast. And every time we crested a hill, we felt our body weight the sensation of the normal force under us decrease because of this effect. Then when we went to the bottom of the hill and we started going this way, what would happen was we're like at the bottom of a vertical circle. We didn't solve that yesterday, but it would be this equation with a plus sign here. So at the bottom, we feel our body weight plus mv squared over r. We crest the hill, body weight minus mv squared over r, plus mv squared over r, minus mv squared over. And it was like a roller coaster. We feel that rising, that's the stomach rising up in you, and that exciting effect that we felt as kids. And we would scream faster, faster, and he would go faster. So to us as little kids, that was brilliant driving. Now to an adult watching that, that'd be crazy driving. So, you know, we enjoyed it as kids. Our uncle indulged us, which was great, but that's partly why we had to keep the story a secret from my aunt. So just a little funny story. She would say, "You're a maniac. What are you doing? You're going to crash." But we loved it. We had a lot of fun with that vertical circle effect. All right. So that's vertical circles 2. I hope you enjoyed the physics. I hope you enjoyed the little story at the end. And I'll see you next time. Back again. Sorry, I got a little carried away with the story and I forgot to summarize. So let me do that because it's important to just look back and make sure we have the main ideas. So we can solve for the critical speed by making no other force but the force of gravity, providing that centripetal force toward the center of the circle here. We could solve for V. So that's one possibility. The other possibility, we could go faster than that speed that we calculate here. And that's the case of a roller coaster or a mass on a string going over the top. If you go faster, gravity's not enough. We need extra force toward the center of the circle. So that's going to be provided either by string tension or normal force. So then we say these two together, we add to get the centripetal force we solve. And then if you go less than the critical speed, then gravity's too much. You would go like this. To maintain that circular arc, you need to lessen that gravitational force. So the support force underneath, opposite over here, it's going to support you a little bit less than gravity. So then the physics is the net force is this minus that, and you solve. So there's the review. Take a look at your notes and make sure you understand everything before you try the homework. All right, now I think I'm really done. So I'll see you next time.